Hello, I'm Sophia, and I developed uniform origami-inspired artificial muscles for prosthetic limbs. For a bit of background, I've been interested in engineering and have conducted a couple of projects over the years. My long-term goal is to make scientific tools more available to as many people as possible, and I'm inspired by clever inventions that simplify sophisticated instruments into simple tools. For instance, the paperfuge, a hand-powered centrifuge made of paper and string, and the foldscope. However, I'm specifically interested in biomedical engineering, in which one of the goals is to improve the functional activities of people who are limited in mobility. I realize that many artificial muscle designs are generally impractical, as I will explain later, so I decided to take on this project. Now for some definitions. Artificial muscles are advanced materials that can be expanded and rotated by external stimuli, such as fluid pressure, thermal energy, and electricity. They have many applications including wearable robotics or soft robotics in general, and transformable architecture, but prominently they are applied in prosthetic limbs. The fundamental design used in this project is the fluidic actuated origami-inspired artificial muscles, or foam for short. There are many artificial muscle designs, but a recent paper introduced foams, which simply consists of a fluid medium, a compressible skeleton, and a flexible skin, and it contracts with negative fluid pressure. It is also important to note that there is no full-fledged model or implementation for the foam-based prosthetic limbs, as they are relatively new. The rationale behind this project is noticing the disparity between the ideal and the reality in artificial muscle design. The ideal artificial muscle is strong, energy efficient, flexible in both motion and speed, easily controllable, light, and inexpensive. In other words, the ideal design mimics or exceeds the functionality of an actual human arm. In reality, artificial muscles struggle between mechanical aspects like strength and practical aspects like efficiency and cosmetics, wherein one or the other is sacrificed. For instance, shape memory alloys produce high stress but are difficult to control. McKibben muscles have high strain but pose safety issues due to their reliance on positive pressure, and the list goes on. It's also important to note that prosthetic limbs are expensive, and the actuator, the artificial muscles, are responsible for a large amount of the cost. Arm devices range from $3,000 to $30,000 as a result of repair and replacements over time. Parts can be worn down and broken, and this occurs naturally because of patient growth and change. The goal is to modify an artificial muscle design and implementation to reduce the issue of full-scale repair to localized repair. For instance, if one part of the muscle is damaged, it can easily be repaired without tampering with the rest of the muscle system. Thus, long-term prices of both prosthetic manufacturing and maintenance are reduced. To evaluate this design among many others, several variables were considered, and these variables can be separated into two categories. The first are the mechanical aspects, and the second are the practical aspects. Mechanical properties include strain, a measure of contraction, strain rate, and strength. Strength, however, was not quantified as all of the involved artificial muscles exceed the normal strength of a muscle and are difficult to quantify across multiple sources. On the other hand, practical properties include efficiency, the ratio between mechanical output and energy input, work density, mass density, cost, and cosmetics, which is a qualitative property that will be discussed later. The fundamental artificial muscle design used in this project is the foam. After many prototypes, the following materials were used for the final product: polyester for the skeleton, low-density polyethylene skin sourced from Ziploc bags, and air for the fluid medium. The dimensions were minimized to allow more flexibility when customizing a prosthetic limb depending on the patient. The end ports are lure locks paired with rubber washers. And hex nuts. This allows simple removal and addition of muscles. Thus, the muscle length can easily be adjusted to accommodate the needs of a patient, and the muscles can easily be repaired. Manifolds composed of PVC pipes allow air movement between all of the muscles and the vacuum tank. complementary lure locks on the vacuum are connected to the origin of the muscle filament, and the insertion points are closed with lure lock end plugs. Solenoid valves are placed in the connection between the manifolds and the vacuum tank. The vacuum tank presents negative pressure to cause contraction of the muscles. The naturally closed valve is activated by a push button that is programmed by an Arduino Uno coupled with an Arduino Shield R3 by a simple C++ program. In other words, when the push button is activated, the valves will open and will cause the muscles to contract. Overall, 10 artificial muscles were involved in this analysis with a range of external stimuli: fluid pressure, thermal energy, electricity, and magnetism. To analyze the data, a chi-square goodness of fit test was used to evaluate all of the aforementioned variables and to rank the muscles. There are two interpretations of artificial muscle performance: similarity, or how closely the artificial muscles resemble a human muscle, and outperformance, a measure of how much the artificial muscles fall short or exceed the capabilities of a human muscle. The artificial muscles with the lowest chi-square sums ranked the highest. The expected or ideal parameters were slightly different for the two interpretations. To assess the muscles for similarity, the ideal parameters were the actual values of a human arm. To assess for outperformance, however, the ideal values were arbitrarily chosen to reflect the best values for that specific property. This table does not show these arbitrarily chosen values, but one example is that ideal efficiency was set to 1.0 or 100%. Ultimately, the foam muscle placed fourth in both ranking lists. The foam had noticeably better values for its practical aspects than its mechanical aspects. Mechanically, strain is higher than the natural muscle, while strain rate is lower relative to the rest. Practically, the muscle is lightweight, inexpensive, and energy efficient, which allows it to be widely used and applied. Overall, the chi-squares for both aspects were balanced. Although the foam does not excel in a particular property except its cost, it ranks highly relative to the other artificial muscles despite it being a new concept and design and despite its low-cost materials. Although cosmetics were not quantified, foams are easily implemented in prosthetic arms because it allows linear contraction without significant lateral expansion, it's concealable, and is not bulky or voluminous. Still, there are more qualitative, non-cosmetic perks to this design. The foams reduce the issue of full-scale repair to localized repair, as mentioned before, and thus long-term prices are reduced. The lure locks and the uniformity of the muscles allow easy attachment and detachment for fast repair. The reliance on negative pressure eliminates the risk of bursting muscles, unlike the McKibben muscles mentioned earlier. And contributing to energy efficiency, passive relaxation in antagonistic pairing reduces the need for supplemental positive pressure and thus supplemental energy input. And finally, the developed foams are easily rearranged and can conform and bend around structures for more types of movement, such as the simple linear contraction shown here and even torque. There are three prominent future goals in mind. The first is to apply environmental friendly yet robust materials. The second is to minimize the space required for the vacuum system, which includes the vacuum tank, the vacuum pump, manifolds, solenoid valves, and control system, and to commercialize the design for widespread use in clinics around the world, from first world to third world countries. Examples of commercialization include developing soft robotics kits for students, and even portable medical kits for soldiers and amputees at war. In summation, this new foam design attempts to address a complex problem, which is how artificial muscles sacrifice either mechanical or practical aspects and seldom exhibit proficiency in both. The original paper for foams focused on introducing a novel muscle design and the potential of its structure. The new foam version preserves its original properties such as simplicity and accessibility, but it takes its potential and is now uniform and miniature to provide a robust yet accessible user-friendly actuator for prosthetic limbs. Since the new foams can be fabricated via common supplies, mass manufacturing of these foams is possible, and thus, prosthetic limbs can be available to patients with less resources, students learning robotics at school, or even soldiers at war zones. But all in all, foams present a solution that encompasses all mechanical and practical dilemmas found in manufacturing prosthetic limbs. This is Sophia Capili, and thank you for your time.